Hello class, week 14, the focus is on proportional reasoning. We will begin with item 1 though, which is a summary of numerical calculations of operations involving fractions. We spent the last 4 weeks building meanings for operations involving whole and non-whole numbers. In the table below, each letter represents a natural number. You should be able to make sense of each statement in this table by using visual representations with specific values. I'm going to justify a handful of the statements below. In particular, I'm going to justify the fact that these 4 statements are all considered numerically equivalent. And you're going to see a variety of ways to model these ways of thinking, but they all yield the same answer. I'm also going to model this expression down here. I leave it to you to test yourself about creating a simple model to represent the expressions you see in this table. All right, so beginning with equivalent expressions, I'm going to start with this expression, a common fraction, and it will be 6 over 3. So the numerator will be 6 and the denominator will be 3. Now there are 2 fundamentally different ways that you might think about 6 over 3. One is to think about 6 divided by 3, and we will do that with a partitive conceptualization. And another is to think about 1/3 of 6. And these 2 expressions are have the exact same meaning. 6 divided by 3 partitively is the same thing as 1/3 of 6. You could also do 6 divided by 3 quotatively and get the same number, but I will just model the partitive way of thinking. We could also think of 6 over 3 as 6 copies of 1/3. Okay, and then I've drawn a tape diagram here that has 6 obvious units in it, and I'm going to do 6 divided by 3 partitively. I'll do 1/3 of 6, which is going to be the same thing, but I'm going to do the partitioning in 2 different ways, hence the 2 different rows you see here. And then here I'm going to do 6 copies of 1/3. All right, to have 6 divided by 3, to split 6 into 3 groups. Well, since 3 divides into 6, this is actually rather convenient because we can rather simply use this line and this line to partition the 6 into 3 equal parts. And then, of course, the focus is the size of one part. And so when I do 6 divided by 3, I get the answer of 2. And of course, this is 6 divided by 3 with a partitive conceptualization. If I do 6 divided by 3 with a quotative, then you would effectively be saying, let's do this. How many 3's make 6? Well, here's 1 3. And here's a second 3. And so you could say 6 divided by 3 quotatively is also 2, because 2 3's make 6. But I'm not going to model the quotative, just the partitive. Now, 1/3 of 6 has the exact same meaning as 6 divided by 3 partitively. So I could redraw what I just did, but I'm going to just show you cross-partitioning here. So when I do 1/3 of 6, you imagine 6 as a new unit. So in a way, imagine that these bars aren't there. So there's 6. That's 6 units right there. It's just one thing now. And I'm going to partition that into 3 parts, but horizontally. So we get these long, skinny rows. And we make that a straight line. There we go. And then I'll just copy that and paste another one. And this is probably good enough. All right, looks good. So we have 3 equal rows. And then I focus on just one of those rows. So there's one part, second part, and a third part. So anyway, I shaded one of the rows. So I've shaded 1/3 of 6. Because I broke 6 into 3 rows, and I shaded one entire row. But if you were to take these pieces and rearrange them, notice that they wind up filling the exact same, oops, that's not what I wanted to move. Notice that they wind up filling the exact same amount, there we go, as doing a vertical partition of 6 into 3 parts. And so we still get an answer of 2. Let me put the shading back where it was though. So one entire skinny row like that still represents a value of 2 units. And keep in mind that one of these blocks represents 1 unit. I haven't specified what the units are, but we need to always be mindful that that's 1 unit. So what's shaded right here is a third of a unit. And here's another third of a unit. And here's another third of a unit. And you can see that we have 6/3 of a unit. So this drawing right here does also represent 6 1/3, which is what I'm going to draw here, but using vertical strips. So here's a unit, and I want to do 6 1/3. So I first have to break that into thirds, but instead of doing it horizontally like this, I'm going to break this into thirds vertically, something like that, and then do 6/3. Well, there's 3/3 right there already, and we need 3 more thirds. And so 6/3 is going to be this amount, which also is 2. So the value of this fraction here we say is 2. And in all of these cases, the 2 is a measurement of units. We have found that there are 2 of these shaded total in each of these drawings. If I do quotative division, I also get an answer of 2, but the answer isn't 2 units, it's 2 groups of 3. So when I think of 6 divided by 3 in a quotative sense, I still get numerically 2, but it's not 2 units any longer. It's not the same thing as shading in 2 of these blocks. So that's why I refrained from modeling 6 divided by 3 quotatively. I went with partitive. And then here's a partitive interpretation as well. And so all of these 2 all have the same unit in this particular case. Okay, now I'm going to model this expression. So I'm going to model this, I'm going to model this and show that you get the same thing. And my choices of A, B, and C are as such. We have 3/2 times 4. So one way to think of 3/2 times anything is to first think of it as doing 1/2 of 4, getting something, and then doing 3 of those. This is what it means to have a fractional multiplier. Do the 1/2 of this first, and then do 3 of, so you partition and then you iterate. Well, according to this statement though, this calculation can be done by just doing A times C and then all over B. So I'm also going to consider what happens if I do essentially 12 over 2, which you can think of as 1/2 of 2 or 12 divided by 2 partitively. You can also do this quotatively, but I'm going to interpret this partitively and then do 1/2 of 12 and show that we get or these have the exact same meaning. So I'm going to do one drawing for that. And then another thing you could do with this particular fraction is, so maybe I should make this arrow look more like this. Another interpretation of that fraction is to do 12 copies of 1/2. So the 3 things I'm going to model is the partitioning followed by iterating. I'm going to model doing 12 split into 2 groups, and I'm going to model doing 12 1/2s. And we're going to see that we get the same result numerically each time. Okay, so let's first do 1/2 of 4. So if I do 1/2 of 4, this is a representation of 4 right here, so each block is one whole. The 4 1/2 I split right there, and then I have half of that shaded. But then I do 3 copies of this. Let me grab this and copy, paste, and then do one more copy, paste, which suggests that we would have 2 more blocks over here. So we have 3 copies of 2 essentially, and that gives me a total of 6. 6 units. Remember, each of these was one whole unit. So if you do partitioning of 4 first, you do 1/2 of 4, you get 2, but then you do 3 2s and you wind up getting 6. Now another way to partition 4 into 2 parts is to do a horizontal cross partitioning. So here's a representation of 4, right? You can effectively, now we're going to unitize and imagine that that's a single thing, even though it's not, it's 4 things. But imagine it as a single thing and do half of it. But instead of doing half of it vertically, I'm going to do 2 rows instead of 2 columns. So when I do the 2 rows, let's split this in half this way. And then focus on shading half of 4. Now what you see there are 4 1/2 are shaded. And that's a total of 2, right? Because there's 1 unit and here's a second unit. So there's 2 units shaded there. But now I want to do 3 copies of that. I'm going to do the copies going down in the row. So here's a second copy, and here's going to be a third copy, which will be essentially another row of halves like that. And each of these rows represents a value of 2. So if you do cross partitioning and then make extra rows, that's another way to model partitioning 4 into 2 parts and then iterating that part 3 times. Now let's do 3 times 4 over 2 and model that. Well, first I'm going to model 3 times 4 by doing 3 rows of 4. So there's 1 row of 4. Oops. Right, then we have a second row of 4 right there, and then we have our third row of 4. So we can see the 12 units sitting right here. And we're going to break 12 into 2 parts. Well, the obvious way to do this is right down the middle. You could do it like this as well, but then you have a bunch of extra pieces. You could do it this way, but I'm not going to. It seems more sensible to split this in half right down the middle like this, and then focus on half of 12. And half of 12, of course, is 6. So 1/2 of 12 is 6, or 6 divided by 2 partitively is 6. All right, and then the last way to think about this is to do 3 or 12 copies of 1/2, so 12 1/2. Well, I've drawn 6 blocks here. I know the answer is going to be 6, so I already drew the 6 blocks ahead of time, but each of these is 1 unit. So I have to model what half of a unit is, so I'm going to split this right down the middle. And then, so here's a half and here's a half. And I want 12 halves. So I'm going to have to keep making more and more halves until I get to 12. So we have, there's 2 halves right there, and then 4, then 6. This gives me 8 halves total, 10 halves total, 12 halves total. And so when I shade 12 halves, we can see that 12 1/2 winds up being the same amount as 6. That was not a very good, we want that to end right there. So we get 6 out of this as well. And so the value of this expression is 6. And as you can see, there's a variety of ways of modeling this and showing that numerically these are the same expressions. If you do a fraction times a whole number, then you can simply just multiply that whole number to the numerator and rewrite your fraction. You can think of these formulas, if you will, that are in this table as just shortcuts for operating quickly with fractions. But the underlying meanings are quite rich in their diversity and the ability to model them, to make sense of them, and why these things are true. Let's move on to number 2, an idea known as multiplicative versus additive comparisons. So we have 2 strips. A red strip is 8 feet long and a green strip is 3 feet long. We're going to compare the 2 strips additively. What that means is what would you need to add to one of these strips, the smaller one, so that it's equal in length to the longer one. So there's going to be another strip here. I'll make it orange. I'm going to figure out how long that is, what's the difference in length between these. This is just an additive comparison. It's a comparison where we would use subtraction to get the value. This is something we've done in the past, so I'm just kind of reminding us of this idea. I'm going to also put in hash marks. Well, I'll do that in the next one, actually. I changed my mind. So we know that this one here is 3 feet. The red one is the green one is 3 feet. The red one is 8 feet. And the difference between these, of course, is 5. So we know that the orange would be 5 feet. And we answer this question doing subtraction. So you would say, okay, we have something that's 8 feet long, and we're going to remove 3 feet. Not remove it, we're going to compare. This is not the takeaway model, it's the comparison way of thinking. And this gives us a difference of 5 feet. So in words, you could say a couple things. You could say red is, I'll just use R for red. Red is 5 feet longer than green. Or you could say it the reverse direction as well, but use the word shorter. Is 5 feet, green is 5 feet shorter than red. So there's a sort of a forwards and backwards way of doing this additive comparison. And subtraction is the way you get the difference. Now we're going to compare the two lengths multiplicatively. In order to do that, I will put hash marks to indicate each foot. So this green one is 3 feet. So we have a starting and an ending, and then I want to break this into 3 equal parts. We'll do that. It's good enough. So that's 3 feet. And the red one is 8 feet. So 3 of those feet will be right there. And then it's got to continue this. Or you could have started with 8 and done 1/2. 1/2 is roughly right here, and then break each of these in half as well. So you should see a total of 8 units there. Okay, so looks good. So we have 8 feet and 3 feet. To compare these multiplicatively, we want to say, this is something we've done in the past, but we're going to say how many times as long one strip is than the other. So let's start with the green and first figure out what it is I have to multiply to G, to the green. So we're going to say, how do I scale the green so that it's equal to the red? So this is what we're trying to resolve. And we can do that by, there's a variety of ways we can do this. So we start with the green. The green is now my new unit. So that's 1G, if you will. We're going to partition down to 1/3 of G. So this is 1/3 of G. And then we can see that the red will be 8 of those. I didn't quite give myself enough space, but the red is 8/3 of G. I'm going to just write it down here. So we know that the red is 8/3 of G. We start with G, we do 1/3 of it, and then we do 8 copies of that third, and that takes us to the length of the red. Now to do the reverse comparison, I'm going to, let me move this down slightly. I'm going to copy this and paste over here. Oops, paste image, there we go. Now I'm going to start with the red and scale it by a certain amount so that I get the G, the green. Well, now the red is 1 unit long. That's my unit, 1R. So one of these subunits, we'll go with this one right here, is 1/8 of the red. Now I have to iterate that 3 times to make the green. So this tells me that the green is 3/8 copies of the red. You do 1/8 of the red and then 3 copies of that. Now you'll notice, again, we've talked about this before, but you'll notice the reciprocal nature. If you're doing red in terms of green, then we get 1 fraction. If we do green in terms of red, we get the reciprocal fraction as the scale factor. Now the way to get these answers, notice I could get these answers even if these didn't represent feet. Like what if each of these units was 1 meter? And the drawings I would have made here would still look the same. It would be 8 meters compared to 3 meters, or 8 centimeters compared to 3 centimeters, or something like that, or 8 miles compared to 3 miles. It really doesn't matter what the unit was originally. The scale factor, we still see that R will be 8/3 of G, and that G will be 3/8 of R. And you'll notice in my answers here, there's no indication that we were ever working with feet in the first place. That's because we've reunitized. I don't care that this G used to be 3 feet. I'm now thinking that is 1G. So G is now my unit. Feet no longer matter. And in this comparison, R is my unit. Feet no longer matter. We're starting with 1R and then partitioning it and iterating apart. So the way to get these comparisons is through division. Another way to answer the question is to take the length of if I'm doing R in terms of G, then I do the R length and I divide it by the g length. And here you will see the units. So r was 8 feet, and g was 3 feet. And if you will, you can see that the feet units cancel, and you get this sort of unitless scale factor of 8/3. We do division. And if I write this as division, it would look like this. It would be, we would take 8 feet and divide it by 3 feet, which is going to be 8/3. And if I want to do the reverse comparison, if I want to know g in terms of r, then I'd take the green length. I would do g. Oops, let me squeeze in here. I would do r divided by g in this case. In this case over here, I would do g divided by r. This would tell me how long g is in terms of r. And the g was 3 feet. We're going to divide that by the 8 feet. And the feet units don't matter. We get this unitless scale factor of 3/8. So looking at this, the two, the additive and the multiplicative comparisons, we see that if you want to do an additive comparison, you use subtraction. You do longer minus shorter, and you get the difference. And if you want to do a multiplicative comparison, there are two ways to do it. You could do the red divided by the green to get one direction of comparison, or you can do green divided by red to get the other direction of comparison. Right? This makes sense with other numbers that don't produce fractions. For example, if I say compare 6 feet to 2 feet, you would say, okay, well, if I do 6 divided by 2, I get 3. That tells me that 6 is 3 times as long as 2. But if I do the other division, I get 1/3, which just tells me that 2 is 1/3 of 6. It's 1/3 as long as 6. And now we want to be able to express these in words. And so let me move these up so I can put a sentence under each. So in words, you would say something like this. The red is 8/3 times as long. Don't put the word longer here. That can be confusing. For example, if I say that, give me something that's 2 times longer than 4, some people will say 8 because they'll interpret 2 times longer as twice as large as. But some people will say, okay, 2 times longer. Well, 2 times 4 is 8, but I have to go 8 longer than 4, and so they'll say the answer is 12. So it can be confusing when you put the word longer here because they do the multiplication, but then they add that to the original. So it's better to say 8/3 times as long as the green. And over here we would say that the green is 3/8 times as long as the red. And again, don't say times longer. That can be a confusing way to say it. Okay, so now we're going to go to two different strips. Suppose the red strip is only 4 centimeters and the green strip is 3/2 centimeters. Well, you can think of, and we're going to do an additive and multiplicative comparison. You can think of the 4 as 8/2. So we have 8/2 here and 3/2 here. So there's still an 8 units to 3 units comparison. So if I were to break this green into 3 equal parts, something like this, it doesn't look awesome, but it's good enough, then each of these parts would be 1/2 of a centimeter. So that the green is 3/2 centimeters. And then, of course, the red would be 8/2, which winds up producing there we go. And so the red is going to be a total of 4 centimeters or 8/2 centimeters. Right? Each centimeter, if I make this longer, is 1 centimeter, 1 centimeter, 1 centimeter, etc. And the green is 3/2. So we have 1 whole centimeter right there, and then an extra 1/2. But notice it's still 3 parts to 8 parts, just like up here was 3 parts to 8 parts. Let me move this down slightly. I'm going to draw this a couple times, so I'm going to take a moment right now and just copy this image before I write more on it. paste that, oops, paste the image. Oops, did that again, paste the image. There we go. Okay, so as far as the additive comparison is concerned, you'd want to just figure out how long this segment is. And so you could break it up into parts like before, and we would say, okay, so the difference between these would be, count them out, we have 5 halves there. And numerically, if you want to just do an additive comparison, then all you have to do is take the longer length, 4 centimeters, and remove the shorter length, 3/2 centimeters, which we can say, of course, is 8/2 centimeters minus 3/2 centimeters, and we get an answer of centimeters. So it's 5/2 centimeters. And I won't write out the sentence, but you would say the red is 5/2 centimeters longer than the green, or you could say the green is 5/2 centimeters shorter than the red. Now, if I'm doing multiplicative comparisons, we do division to answer the multiplicative comparison. So let's just do one length divided by the other, and then we'll figure out which drawing it's more appropriate for. So I'm going to do the red length divided by the green length. And the red length was 4 centimeters. We're going to divide that by the green length, which was 3/2 centimeters. And I'm just going to use the algorithm. The centimeters, we'll get a unitless scale factor here, so I'm not going to worry about centimeters any longer. But 4 divided by 3/2 is the same thing as 4 times 2/3, and 4 times 2/3 is 8/3. If I do the other division, oops, let's do G divided by R. That's going to be 3/2 centimeters divided by 4 centimeters. Again, the centimeters will not matter. Get a unitless scale factor here. This is just 3/2 divided by 4, but to divide by 4, you multiply by its reciprocal. And that, now we can just multiply across using our shortcuts and get 3/8. Okay, now which of these goes with which drawing? This is sometimes where students will get confused. Which one is 8/3 as long as the other one? Is it R equals 8/3 G or G equals 8/3 R? Well, when you do R divided by G, you're essentially saying how many G's make R. So you're measuring R in terms of G. So it's like starting with G, doing 1/3 of it. Notice this is 1/3 of G. Even though it's a 1/2 centimeter in length, it's only 1/3 of G. If you think of G as 1 unit, that's 1/3 of G. And then, of course, the R will be 8/3 of G. So when you do R divided by G, you're actually figuring out how to measure R in terms of G using a quotative meaning. Right? How many G's make R? That's a quotative meaning for division. And so we can conclude that the R is 8/3 of G. It's 8/3 G's that make R. And then over in this one, it's going to be the opposite direction. When I see this division, think quotatively, how many R's make G? So in other words, what do you do to R to make G? So if I think of R as 1 unit right there, and I break it down into 8 equal parts, so that would be 1/8 of R. And so the G will be 3/8 of R. So notice one of these little strips, in this situation, we found 3 different ways to measure that length right there. It's either 1/2 of a centimeter, it's 1/3 of G, or it's 1/8 of R. This is 3 instances of unitizing. We're focusing on 3 different units each time, and so that's why we get 3 different fractions, 1/2, 1/3, and 1/8, but they all represent the same amount. And so our conclusion here then is that the G is equal to 3/8 of R. And again, I won't write out the sentences. But that's how you do multiplicative comparisons. You do division, and to do an additive comparison, you do subtraction. Okay, now let's talk about ratios, proportions, and rates. The words ratio and rate are used in various ways by mathematicians and educators, which can lead to much confusion. For this class, we will adopt the definitions used by the Arizona State Math Standards. Thus, a ratio is a multiplicative comparison between the values of two quantities, whether the values have the same unit or not. The value of a ratio of A to B, and that's how that's said, and you say the ratio of A to B, those are the two values being compared multiplicatively. And the value of that ratio is simply the quotient A divided by B, and I'm going to emphasize with a partitive conceptualization. Okay, there's a lot there to digest. Let's do two examples. One example, we're going to have the two values be of different types, have different units. One's dollars, one's pounds. And the other one, we're going to do a ratio that's cups to cups, so they have the same unit, even though it's cups of water versus cups of flour, but there's measuring volume and they're both the same unit. So different units, same unit, and see how to do the value of a ratio. Okay, to calculate, so the A and the B, the A in this case is the $24 and the B is the 6 pounds. Right, so to find the value of a ratio of A to B, you simply do the quotient with a partitive conceptualization. So what I'm going to do is simply do $24 and divide it by 6 pounds. And this gives me a $4 per pound. I'm not going to model this with a picture, but it's essentially like breaking $24 into 6 groups, where each group represents a pound. There'd be $4 per group, or $4 per pound. And that's a partitive conceptualization. Notice that it's the, if I were to place this into the structure of a multiplicative structure, remember that partitive division finds a missing multiplicand. So this number, this 4 is a multiplicand. So it would be $4 per pound would be in the multiplicand position. Then we need a multiplier and then a product. Let me make this look a little bit better. Okay, so which number goes in the role of the multiplier is going to be whatever has the unit that matches that denominator unit, pounds. So the multiplier is the 6 pounds, or you can think groups, if you will. 6 groups of $4 equals $24. And here's our multiplicative structure. But notice that the value of the ratio is a multiplicand. This is our answer to the question. We found the value of this ratio, and it's a, let's write this. Value of ratio is a multiplicand, because we're doing division but with a partitive meaning, so that means we're finding a multiplicand. Now in the case where we have the same units, we can still do the same interpretation. So this one's phrased a little bit differently. It says the ratio of cups of water to cups of flour is 2 to 3. Another way to say that is just put 2:3. You'll see that notation often. Find the value of this ratio. Okay, so our A is 2 cups of water and our B is 3 cups of flour. So the division I'm going to do is going to be 2 cups, and I'll just put C for cups of water. So CH2O, that stands for 2 cups of water. We're going to divide that by 3 cups of flour. I'll just do F for flour. So that's cups of flour. And the division gives us 2/3. And the units of this multiplicand are cups of water to cups of flour. In a multiplicative structure, it would look like this. We would have a multiplicand of 2/3 of cups of water to cups of flour times the multiplier should have units of cups of flour, so it's 3 cups of flour, and then the product is the units of cups of water, and this gives us 2 cups of water, 2 cups H2O. And I'm going to do a little bit of a visual here with this, because to interpret this 2/3 cups water per cup of flour, this is saying that if you have a cup of flour, we'll use a block for the flour, say that's 1 cup of flour, you would have only 2/3 That's horrible. Let me do this. I'm going to draw another box. Break it into thirds, and this is the water, the H2O. I don't know why I'm doing H2O. I should just do W for water. It's less writing. Cups of water, cups of water, cups of water, cups of water. So this was our flour, this was our water. And let's emphasize so we have 1 cup of flour, and corresponding with that is 2 cups of water. Or sorry, 2/3 of a cup of water. So that's what, when you see this expression right here, this is saying 2/3 cups of water for every cup of flour. And then of course, if you were to triple this, I'll just triple that, so that we had 3 cups of flour, you can see that when you combine these portions here to see how much water you're going to have, or you could take this one here and split it up and fill in that empty spot and that empty spot, so you would see that you would have 2 complete cups of water corresponding to 3 cups of flour. But anyway, the value of the ratio is, the answer to this question was right here. And the same thing I said about the value of the ratio is a multiplicand, even when the units are the same, cups and cups. There are other ways to think about this, but I prefer to think of the value of a ratio when you do this division right here, that you imagine it in a partitive sense. Okay, now sometimes the value of a ratio remains constant as the 2 quantities covary, in which case we say the 2 quantities are directly proportional to each other. Sometimes we would leave the word directly off. Determine whether the following situations entail proportional relationships. Okay, so let's say that we buy 6 pounds of oil, we paid $24. And then we buy 12 pounds of oil later, maybe, and we only pay $36. Let's see if the ratios remain constant. So I'm going to make a table. I'm going to put the weight, make a little small table here, the value, and then we're going to do a ratio of, let's do a ratio of value to weight. Okay, make a small table. All right, so when the weight was 6 pounds, we paid $24. I'll just leave the units out of my table. And the value of the value of the ratio of value of the oil to weight of the oil is, we do 24 divided by 6. I'm leaving the units off, but the answer will be 4. And I'll put the units on now. $4 per pound. Okay, notice this is the same situation up here. And later, we buy 12 pounds of oil, and we pay only $36. And so when I do this ratio, I do 36 divided by 12. That's going to give me $3 per pound. Notice the ratio did not remain constant, even though we created a new instance of values. Right, so we say that the values covaried, so that the weight changed, it varied, and the value changed, it varied. And so we generated a second instance of paired data, $12 pounds to $36. Be mindful that when I'm talking about quantities again, I'm using the definition of quantities we've talked about in the past. So I think of weight as a quantity and value as a quantity. Oops. All right, so those are the 2 quantities, value and weight. And the numbers are not quantities themselves, they're values of quantities. They are specific instances of that quantity measured with a certain unit. A lot of people, if you say, hey, write down a quantity, they'll write down like a number. But I'm using quantity much more generally. Quantity is something that can be measured, even though you haven't measured it yet. So weight and value are the quantities, and they covary, meaning they vary in tandem. If one varies, the other should vary. But when you did the 2 instances and calculated the 2 ratios, we got unconstant. The ratios changed. So the ratios were not constant. So I would say that the weight and value are not proportional to each other in this case, because to be proportional to each other, they have to maintain the same ratio. And you might ask yourself, well, how come what happened here that we paid less the second time per pound than we paid the first time? Well, this might be easily answered with bulk purchases. Sometimes when you buy a lot more of something, they will give you a better deal. And so it's not always the case that the amount of something that you buy and the amount that you pay for it are proportional to each other, because you get discount if you buy more and more sometimes, like that clearly is happening here. But let's say that doesn't happen. You don't get any bulk discounts. And so notice how this one's phrased. You're going to pay $24 for every 6 pounds of oil. This isn't saying that you pay 6 pounds once and pay 24 once, and then later maybe you get a different rate. This is saying that no matter what, you come into the store, you're going to pay $24 for every 6 pounds. So if I were to repeat this table, just copy all that. Oh, let me make a conclusion over here as well. We're going to say weight and value are not proportional or directly proportional. I don't like that horrible handwriting, but you get the idea. Let me just proportional. And let's see what conclusions we've reached down here. So now you're paying $24 for every 6 pounds of oil. So we have to make a few edits. That's not going to be the correct price any longer. Let's see what happens. If you paid for 6 pounds, you paid $24. So if you wanted to buy 12 pounds, then of course you're going to pay $48, because it's $24 per every pound. If you do 48 divided by 12, we still get the $4 per pound. If you buy different amounts, right, if I were to squeeze another data in here, what if you only bought 3 pounds? Then you would expect to pay, only $12 for 3 pounds, but you're essentially paying $4 per pound. And if you do 12 divided by 3, 12 divided by 3, you're going to get, again, $4 per pound. So the ratios are constant. They are not changing. Which means, in this case, weight and value are proportional. So it just depends. Do you offer bulk discounts or not? If you offer bulk discounts, then you have two quantities that are not proportional. If you do not offer bulk discounts, you maintain the same price no matter how much you buy, then you would say that the weight and value are proportional. Now, a unit rate is the value of a ratio corresponding to a proportional relationship. Every proportional relationship entails two reciprocal unit rates. So the same situation, you paid $12 for every 6 pounds of oil. Let's do a ratio of, I'm going to repeat the ratio of value to weight. All right, so let's do a ratio of value to weight. That means we take the $24 value and divide it by the 6 pounds of weight. With a partitive conceptualization, and we get the $4 per pound. Let me write it this way, $4 per pound. This is called a unit rate. It's $4 for every 1 pound. Okay, so another way to think of that is $4 for for 1 pound. You can also do the other way around. You could do the reverse ratio, right? So effectively, we're going to do the ratio of weight to value. There we go. Get that ratio of weight to value. In which case, you would switch these around as well. Instead of dividing, you'd divide the 6 pounds by the $24. And 6 divided by 24 is 6/24, and 6/24 is 1/4. So we get a reciprocal answer here, 1/4, and the unit is a reciprocal unit. It's pounds per dollar. So this is saying that for every $1 that you have, you can only buy a 1/4 pound. So 1/4 pound for $1. These are called unit rates because it's a value of one quantity compared to the value of only a single amount of the other quantity. So the fact that you have ones on each side over here makes these called unit rates. $4 per 1 pound, a 1/4 pound per $1. All right, number 4. Now we're going to start doing some proportional reasoning. You paid $24 for every 6 pounds of oil. Notice how I phrased it. You paid $24 for every 6 pounds of oil. So there's no bulk discounts here. So we do have a proportional relationship. We're going to use a variety of strategies to fill in the missing entries of this table. Okay, so we have I put the data here that was given. 6 pounds of oil corresponds to $24. And if I want to answer this first question right here, there's a variety of ways in which you can do this. First way is to recognize that we have a multiplicative structure. So we could set this up as a multiplication problem. You can put a question mark right here and say, okay, well, I know that our basic structure is we do the weight of the oil in pounds. So we have some number of pounds. We multiply that by one of our 2 unit rates, whichever one is relevant. If I put pounds as the multiplier, then I want to go with the unit rate that has pounds in the denominator unit. So I want that one. All right, wouldn't it make sense to put this one next? So let's do the top unit rate, so $4 per pound. And this gives you some amount of dollars. The other option is to do some amount of dollars, multiply it by the other unit rate, so 1/4 pound per dollar, and that gives me some number of pounds. These are your 2 basic multiplicative structures. It really doesn't matter which one you use. If I'm trying to figure out, if I know that I want $12 worth, then I can do the top one and put a 12 right here, and then solve this missing multiplier problem by division, do 12 divided by 4. Or I can put the 12 in this position as a multiplier and do a missing product multiplication task. Right, so the question mark right here, this question mark will be answered by finding this number in this position or by finding this number in this position. So you have a variety of options here for setting up some sort of multiplicative structure. The unit rates belong in the multiplicand spots, and then the extra data we have about the value of $12 will either be here or here, depending on which structure you work with, and then you're just left with finding either a multiplier or finding a product. So this is one way to do it. Now the answer, of course, is going to be, in each case, 3. Right, because you're saying 3 times, or what times 4 will give me 12? The answer to that's 3. You know, a quotative division will answer that. Or you can say, just do a flat up 12 copies of a 1/4. That gives me 3 as well. And so we get 3. Now we're going to work on very efficient ways of filling in the rest of these. So I'm not going to use a multiplicative structure for every single one of these blanks. I'm going to show you some clever ways when you have 2 proportional quantities, some clever ways that you can get extra entries in a table. Okay, one of them is by moving across the table from column to column. If I want to convert weight to value, go this direction in the table, then I need to multiply the weight times, multiply it by, I can't zoom in any more than that. Let me move this up a little bit. I need to multiply by 4. Let me change, I want to be able to write a little bit smaller, so I'm going to change the thickness of this pencil. Okay, so to go this way in the table, we multiply by $4 per pound. So these are the conversion. If you multiply 6 pounds by $4 per pound, I get $24. To go backwards in the table, to go from right to left, from one column to the next column, I would multiply by the other unit rate, which is everything is reciprocal. So multiply by 1/4 instead of 4, and it would be pounds per dollar instead of dollars per pound. So if I take 24 and I multiply it by 1/4, I get the 6 if I want to go that direction. This relationship can be used to generate any new row you want, right? So before we did not know this, but I did know 12. So I would do 12, and to go this direction I would use the green, multiply it by 1/4, and that would give me the amount we need right here, which is 3. So that's one way to get this. To get the next entry, I can continue this pattern because the unit rate remains constant from row to row. That's why these are proportional. It's always the same unit rates. The ratios do not change. But to go from 9 and then to figure out what we need to put right here, we use this unit rate, right? We do 9 times 4. That gives me 36, right? 9 pounds times $4 per pound would give me a total of $36 to buy 9 pounds. All right, so this multiplicative, these unit rates can be used to convert from left to right for every entry of the table if you want. You can use them all across here. That's one way to fill in the table. Another way is we can do something called tandem scaling. If two quantities are proportional, then if you scale one amount by a certain factor, so notice to go from, we'll pretend we didn't know the 3 yet. So to go from 12 to 24, ask yourself, what scale factor would you multiply 24 by? And that would be a scale factor of 1/2. So if I do 1/2 times, notice where I put the x. I'm putting the x here to suggest that I do really 1/2 times 24. In other words, the 1/2 is in the multiplier position. And so I'm thinking of it as a unitless scale factor if you want to think of it that way. So we're going to scale, I'll put the next to the arrow, we're going to scale 24 by 1/2. That turns it into 12. Well, you just do the same thing over here. Scale 6 by 1/2, and that turns it into 3. This is called tandem scaling. You just scale each amount by the exact same amounts, and you can create another entry in this table. Okay, let's pretend we didn't know the 36 yet and use tandem scaling. Well, once I know that $3 or 3 pounds of oil corresponds to $12, I can do some more scaling. I would do, what do I have to do to 3 to turn it into 9? I could do 3 times 3. Putting 3x means we're doing this essentially, 3 times 3. And I'll do the same scaling over here, 3 times 12. And 3 times 12, of course, is 36. Another way you could do this, if you know a pair of values here and you know a second pair of values, right? If it costs, to buy 6 pounds of oil costs $24. To buy 3 pounds of oil costs $12. So it's also possible you can add 2 rows together to create a new row, right? If you want to buy a total of 9 pounds, just add those. You get 9 pounds. We'll just add the corresponding prices. You'll get $36. So you can also add rows to make new rows. But I'm not going to emphasize that much. I want you to think of scale factors instead of just adding rows. Let's try to think more multiplicatively instead of additively. You can also go straight from the 6 to the 9 with a scale factor. Notice where I put the x, just as a quick comment, notice where I put the x, I put it in front of the 4. So I'm saying that I would do 6 copies of $4, 6 pounds times $4 per pound. That's how I would generate the 24. But if I go the other direction, notice where the x is, I would do 24 times 1/4. So I do $24 times a quarter pound per dollar, and that's how I would generate the 6. So where I'm placing the x's in my little notes here is important, because it's identifying which number I think of as the multiplier and which number I think of as the multiplicand. It's also possible to scale 6 straight to 9. I don't have to go through 3. You would ask yourself, okay, what would I multiply 6 by to make 9? Well, the answer to that is quotative division, 9 divided by 6. So if I do a quick, hey, what's 9 divided by 6 quotatively? In other words, how do I scale 6 to 9? And that's just 9/6, which is just 3 halves. So if I do 3 halves times 6, right? If I do 3 halves times 6, that's doing a half of 6, which is 3, and then do 3 of those, that's 9. So 3 halves times 6 will produce 9. And you simply, let's delete that, you simply do the same thing to the 24. Right, so if you want to go straight from the 24 to the 36, then you're going to do 3 halves times 24. So when I do 3 halves times 24, I do half of 24, that's 12, and then 3 of those make 6, or makes 36. Okay, let's say I want a 1 here. Lots of ways to get a 1 there. Let's do a new comparison. Let's start with the 36 and go down to the 1. Or you can start with the 12 and go to the 1. Or you can start with the 24 and go to the 1. It really is up to you. Just so I don't have arrows all over the place, I'm going to start with the 36 and scale it down to 1. Well, what do you have to multiply 36 by to make 1? Well, the answer is you're going to multiply by 1/36. Right? If I do 1/36 of 36, that'll make this 1. We'll just do the exact same scaling over here. Multiply by, scale it by 1/36. I'll do the work over here, right? If I do 1/36 times 9, that's just going to give me, using our shortcuts, 9/36, which just boils down to doing we get 1/4. So 9 times 1/36 takes you to 1/4. Another way I could have done this is to grab this conversion, right? Take $1 and multiply it by 1/4 pounds per dollar. And that 1 times a quarter, right, will give me that quarter. Right, you can always use these to go across the columns of the table, but if you want to alter the rows of the table, you do tandem scaling. Okay, let's do, how do I go from 1 to, if we have, oh, notice that this just revealed the unit rate, by the way, because one of the two numbers is a 1. So this is saying that 1 unit rate is our 1/4 pound per dollar, which is something we already knew. This is going to reveal the other unit rate, how many dollars per 1 pound. And if I use tandem scaling to do it, to turn 1/4 into 1, I need to do 4 copies of that. We'll just do the same thing here. Do 4 times 1, and that gives me 4. And this pairing is the other unit rate, right? $4 per 1 pound. So the unit rates can be revealed in this table as long as one of the two entries is a 1, and that happens here and here, then you have the unit rates revealed. Right? This 1/4 is the green 1/4 up here, and this 4 is the red 4 here, the unit rates. Unit rates are nice because once you have, the scaling is super easy once you have a unit rate. For example, what if I want to now do, okay, how much oil can I buy with $10? Well, start with the 1 and scale that. It's easy to scale 1 into 10. Right? So to do this scaling, I would do 10 copies. 10 copies of 1. We'll do the same scaling right here. Do 10 copies of a quarter. Multiply by 10. And so that takes me to, let's do that over here. We do 10 copies of a quarter. That's not 10 and a quarter, that's 10 times a quarter. That's 10 quarters. That's 5 halves. So in other words, you can buy 5/2 pounds of oil for $10. And 5/2 is of course 2.5. What if we had an 8 here? Right, to start with 6 and to go to 8, there's a few ways you could do that. You could first divide 6 by 3 to get 2, and then multiply by 4 to get 8. So you could do a 2-step process from 6, or think of dividing by 2 and then dividing by 3 and quadrupling. Right, to go from 6 straight to 8, I would multiply by 8/6 or 4/3. I just divide 8 divided by 6, and I'll answer that question. Or I can use the let's go ahead and use this 1 here, because it's easy to scale 1 to 8. How do you scale 1 to 8? Multiply by 8. So we'll do 8 copies of that. We'll do the same thing from this row to that row. Do 8 copies of 4, and we get 32. Which makes sense, right? If one pound costs $4, and 8 pounds, of course, is going to cost $32. What about the zeros? What if you have 0? Right, use one of these scale factors. Use that one. If you have 0 pounds multiplied by $4 per pound, you're going to get $0. Right, so you can use one of the unit rates to go straight across. That makes sense. It costs nothing to buy nothing, essentially, is what that's saying. And then what if I go to variables? What if I say W stands for the weight and V stands for the value? I'm going to use, zoom out a little bit. I'm going to use these to go across the tables down here. So if I want to go from W to value, from weight to value, I multiply by 4. So I would write down W times 4. And numerically, you could just say 4W if you want. But the real proper structure here is that you do, if you want to find the value, so V dollars, you do that by calculating, you do W pounds, and you multiply that by $4 per pound. Right, so we have our traditional multiplier, multiplicand, and then product. So this is our basic structure. That's why I like to write W times 4, just to keep the multiplier and multiplicand in the correct order. But numerically, it's the same thing as just 4 times W. And then, of course, if you want to go the other direction, do that. If I know V and I want to find W, then multiply by 1/4. So I would say V numerically. In other words, we're saying that to find the weight in pounds, W pounds, I take the value in dollars and I multiply that by the 1/4 pounds per dollar to the correct weight. So the two equations, without all these units in place, oops, I don't know what happened there. Okay, the two equations are really V is equal to 4W, or you can write this as W is equal to 1/4 of V. This is where you take the units out and just put the number in front of the variable and think more numerically. But these are the two equations, the two relationships. Okay. All right, so we've used a variety of strategies to fill in all the missing entries of this table. Now we want to plot the relationship between weight and value. I have two different plots because it just depends on which axis you want to be W and which one you want to be V. Let's do this one here. This will be the weight axis, and this will be the value axis. You can plot just a few points, like we know that 0, 0 is a point, right? And that's just plotting this point in our W is 0 and V is 0. We knew that when the weight was 6, we paid $24, so there's a point up here. When W is 6, V is 24. We knew that when W was 3, W value was 12. And we had some extra data. But what winds up being the case is you wind up producing a linear relationship, which is what you would get if you use a little bit of algebra and you graph this one right here, V equals 4W. You get a line whose slope is 4. If, for those of you who are familiar with algebra, which I think all of you are, you can connect this to algebraic thinking. and you have the graph of a line that starts at the origin. Notice the graph does not, we don't bother making the graph go through the origin into the second quadrant or third quadrant, just because we're assuming W and V are only positive numbers. So this is a ray. A ray is a half of a line, if you will. It starts at a point and then just goes one direction. And every single point on this line represents another pairing, right? So this would say that, okay, here's a point right here. It's 2, 8. It would say that if you wanted to buy 2 pounds, you would pay $8. And every single point represents another pairing. 1, 4. This reveals the unit rate. If you want to buy 1 pound, you pay $4. You can even go halfway, right? You can put a there and say if you want to buy a half a pound, you pay $2, etc. Every single point represents a possible purchase and how much you would pay for it. If you wanted, you can also do it the other direction. You could put value horizontal and put weight vertical. And now we know that our points would just all the x and y coordinates would be backwards. And several of our points would look like this. And you would have a line going through that data like that. Which axis you make horizontal, which one you make vertical. Okay, one last problem. Suppose a recipe calls for a ratio of 2 kilograms for every 3 kilograms. So this one up here, we had a ratio between dissimilar units. Here we're going to do a ratio between similar units, both kilograms, but one's of flour, one's of water. Suppose a ratio of 2 kilograms flour for every 3 kilograms of water. All right, so this will be a proportional relationship. The for every reveals that. So the ratios will remain constant. Find both unit rates. Okay, let's do the unit rate. Let's just do both divisions, essentially. And this will find both unit rates. So we're going to do 2 kilograms of flour, kilograms of water. Same type of quantity. They're both kilograms. Yes, one's of water, the other's of flour, but they're both parts. We're going to use this way of thinking to fill in the missing entries of the table below. Okay, so let's go with the amount of flour. I'm going to show you a strategy here. Flour to water. Parts. Ounce, 1 pound, it's just a part. And flour has 2 parts. So I'm going to copy this and paste. So here's a 2-part structure. Water has 3 parts. So this represents 2 parts to 3 parts ratio, and inside these boxes you can put any amount. You can put in each box. That would correspond to 3 kilograms of water. Did I get that ratio right? It's flour to water is 2 to 3. Oh no, I made a typo here. I went backwards. Darn it. Notice this was 2 kilograms of flour to 3 kilograms of water. Oh no, sorry, I didn't mess up. This is still flour to water. Same order, flour to water, 2 to 3, flour, water, 2 to 3. Okay. Of flour corresponding to 3 parts of water. Okay. And you are totally free to put in any amounts in any way you want to measure here. You can say, let's do volume, 1 cup, 1 cup. So do a cup and a cup and oh no, sorry, these are weights, not volumes. You do have to be careful about that. These have to be weights because a cup of water doesn't necessarily weigh the same amount as a cup of flour. So you would mess up the proportions if you went to volume. So these have to be weights. This is very important to keep in mind. So you can fill in the volumes. Okay, if we set this up that 2 cups of flour for every and 2 cups of water, that'd be a different situation. That'd be volumes we're comparing, not weights. So you can put any weight you want in these boxes. You can put 3 pounds, and then each of these would get 3 pounds. So you would say if I use 6 pounds of flour, then I will need to use 9 pounds of water. Right? You put in any weight you want inside these boxes. And that would give you one of your instances of the covariant quantities. Okay, so if I say the total weight of flour is 2 ounces, well, I have to put 2 ounces into these boxes here. So I would put 1 ounce in each, right? 1 ounce in each. Doing 2 to 3 parts, 2 parts to 3 parts, and we're thinking of weight, right, not volume, then if I put 2 here, then I just put 3 here, whatever the unit is, as long as it's a unit of weight. And of course, the total would be just add those together, and we get 5 ounces total. If I put 2 pounds, that would just be put a pound in each box, right? So there'd be a pound in each. Doesn't matter what the unit is, as long as it's a measurement of weight. Volume. So don't do cups or gallons, that wouldn't work out. 4/5 kilograms. Okay, so if I want the total of flour to be 4/5 kilograms, then I know that each part will be 2/5 kilograms. Right, so that would just, be repeated in all of these. All right, so that I have 4/5 kilograms of flour, and I'd have 6/5 kilograms of water. Would be just add those together. 4/5 plus 6/5 would give me 10/5, so I'd have of the combined amounts. What if I had 12 pounds of water? Well, I want 12 pounds to correspond to these 3 parts, which tells me I need to put 4 pounds per part. Right, because if I got 4 pounds here, then it's here and here. So there's 12 pounds of water here, but there would only be 8 pounds of flour that correspond to that. Okay, so I'm going to put 8 pounds right here. And then the total would be 20 pounds. Okay, if I use F for the total weight of flour, that means there would be 1/2 of F in each box here for flour, so that the total was, each part has 1/2 of F. So then how much water is there? Well, there'd be 3/2 of F. Or we could use a unit rate as well up here, right, to convert water. Rate, that's going to be this one, divided by 3/2. And then the total, in terms of F, would be, what's 1 plus 3/2? It's 1 F plus 3/2 Fs. That's going to be 2/2 Fs plus 3/2 Fs. We're going to have 5/2 Fs. Whatever that F number was, standing for an amount of flour, in weight, a weight of flour. What if I have the W for water? Right, so if all of this here is W, then each part would be 1/3 of W. Right, each part would be 1/3 of W, so the flour would be 2/3 of W. Right, to go this direction, we multiply by the other unit rate, multiply by 2/3. Now I want to add 2/3 plus 3/3, and I get 5/3 total of W. And then finally, we have 8 kilograms total. We can use this image to help us with this. The total is 8. All of that is 8. Then there's 5 parts there. So break 8 into 5 parts, and you would have 8/5 per part. That way, when you put the 5 parts together, you have a total of 8. So the flour will have 2 8/5. And the water will have 3 8/5. Okay, and this